खुद गर्जी, लब ना मत रमे ना बिसरी कैसी तेरी खुद गर्जी, तुझे प्रीत पुरानी बिसरी मस्त मौला मस्त कलंदर, तू हवा का एक बवंडर, मुझके यूं अंदर ही अंदर क्यों रहेगा।
मुझको पुकारे तेरी परछाइयाँ, कबीरा मान जा। केसरिया तेरा इश्क है पिया, रंग जाऊं जो मैं हाथ लगाऊं, दिन बीते सारा तेरी फिक्र में, रैन सारी तेरी खैर बनाऊं। चलना मेरे आ मेरे आ, चलना मेरे आ मेरे आ, चलना मेरे आ मेरे आ बेलिया ओ पिया। ओ पिया। कुछ भी नहीं है ये जहां, तू है तो है इसमें जिंदगी। अब मुझको जाना है कहाँ के, तू ही सफर है आखिरी।
कि तेरे बिना जीना मुमकिन नहीं, ना जीना कभी मुझको तू पास नहीं, मैं तुझको इतना चाहती हूँ कि तू कभी सोच ना सके।
तेरे लिए दुनिया छोड़ दी है, तुझ पे ही सांस आके रुके, मैं तुझको कितना चाहता हूँ कि तू कभी सोच ना सके।
किस्मत से हम आप हमदम मिल गए, जैसे कि दुआ को अल्फाज मिल गए। सोचा जो नहीं वो हासिल हो गया, चाहूं क्या कि खुदा दे अब मुझे।
रब से मिला एक अयान बन गए, ख्वाबों का मेरे मकान बन गए।
आपकी तारीफ में क्या कहें, आप हमारी जान बन गए।
हाँ हम बदलने लगे, गिरने संभलने लगे, जब से है जाना तुम्हें तेरी ओर चलने लगे। हाँ हम बदलने लगे, गिरने संभलने लगे, जब से है जाना तुम्हें तेरी ओर चलने लगे। हर सफर हर जगह हर कहीं बन गए, मानते थे खुदा और हाँ वहीं बन गए। हाँ हंसी बन गए, हाँ नमी बन गए, तुम मेरे आसमां मेरी जमीन बन गए। एहसास की जो जुबान बन गए, दिल में मेरे मैं तेरे लिए दुनिया छोड़ दी है, तुझ पे ही सांस आके रुके, मैं तुझको कितना चाहता हूँ ये तू कभी सोच ना सके। तेरे लिए दुनिया छोड़ दी है, तुझ पे ही सांस आके रुके, मैं तुझको कितना चाहता हूँ ये तू कभी सोच ना सके। जानते ही नहीं अब लोग तन्हा मुझे, मेरी निगाहों में भी है ढूंढते वो तुझे। पहचानते ही नहीं अब लोग तन्हा मुझे, मेरी निगाहों में भी है ढूंढते वो तुझे। हम थे ढूंढते जिसे वो कमी बन गए, तुम मेरे इश्क की सरज़मीं बन गए, वादी बन गए, हाँ नमी बन गए, तुम मेरे आसमां भी ज़मीं बन गए। आई ऐसी रात है जो बहुत खुश नसीब है, चाहे जिसे दूर से दुनिया वो मेरे करीब है। कितना कुछ कहना है फिर भी है दिल में सवाल कहीं, सपनों में जो रोज कहा है वो फिर से कहूँ या नहीं। आँखों में तेरी अजब सी अदाएं हैं, आँखों में तेरी अजब सी अदाएं हैं, दिल को बना दे जो पतंग साथे ये तेरी वो हवाएं हैं। मैं तो तेरे नाल ही रहना जी, हर गम तक तेरे कहना जी, जो रब से कहा ना जाए वो मुझको बस तुझसे कहना जी। सोना सोना इतना भी कैसे तू सोना, सोना सोना इतना भी कैसे तू सोना, तेरे इश्क में जोगी होना मैं हो जोगी होना। तेरे नीले नीले नैनों से शबनम पी लूं, तेरे गीले गीले होठों की होश बातों का अक्सर नहीं था, दिल हमारा तो शायर नहीं था। तूने लिख दी ये तकदीर, वरना इश्क वाला मुकद्दर नहीं था। छोटे हैं दिनों पर, लिए जा तू लिए जा, अभी कुछ और सितम नहीं संभला, दिल मेरे संभाले, इसे कर डाला तेरे हवाले। तू मिटा दे या चाहे बचा ले, जा इश्क पे मेरे चला ले अपनी मर्जी। हजारों दफा आपको फिर बेकरारी कैसी है, संभाले संभलता नहीं ये दिल, कुछ आप में बात ऐसी है। कचले तो ज्यादा काले लगते हैं उजाले, तेरे बिन होए माहिया, ठंडियां हवावाइयां निंदरा उड़ा ले गईया, अख ना तू आके देख ले ओ मेरे रातें कितनी सारी तेरी यादों में गुजारी सोनिए सोनिए तू आके देख ले ओ मेरे रातें कितनी सारी तेरी यादों में गुजारी सोनिए सोनिए कचरा सियाही दिन रंग जाए तेरी कसूरी रैन जगाए मन मस्त मगन बस तेरा नाम दोहराए मन मस्त मगन बस तेरा नाम दोहराए चाहे भी तो भूल न पाए मन मस्त मगन बस तेरा नाम दोहराए मन मस्त मगन तेरा नाम मैं तो यूं खड़ा किस सोच में पड़ा था कैसे जी रहा था मैं दीवाना चुपके से आके तूने दिल में समा के तू छेड़ दिया कैसा ये फसाना मुस्कुराना भी तुझी से सीखा है दिल लगाने का तू ही तरीका है एतबार भी तुझी से होता है ना होश में मैं कभी बाहों में है तेरी जिंदगी नहीं था पता कि तुझे मान लूं या खुदा कि तेरी गलियों में इस कदर होगा हर पहर सुन मेरे हमसफर क्या तुझे इतनी सी भी खबर कि तेरी सांसें चल जिधर रहूंगा बस वहीं उम्र भर रहूंगा बस वहीं उम्र भर है हाथ न छूटे रांझा वे साथ टूटे रांझा वे मैनू तो बस दीदार तेरा लाख कहाना माना वे कैसा दीवाना वे कब से गए है इंतजार तेरा ओ दरिया जरा थम तो जाए तुम्हारा यार रांझा मेरा आया रांझा मेरा ओ दरिया मेरा पीर मेरा हकदार आया रांझा मेरा आया रांझा मेरा दुनिया ज़माना झूठा बताना जीने मरने का वादा सच्चा मेरा
शीश महलना मुझको सुहाए
तुझ संग सुखी रोटी खाए मन मस्त मगन बस तेरा नाम दोहराए मन मस्त मगन बस तेरा नाम दोहराए चाहे भी तो भूल न पाए मन मस्त मगन बस तेरा नाम दोहराए मन मस्त मगन तेरा नाम कच्ची डोरियों 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 से मैनू तू बांध ले पक्की यारियों 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 में होंदे ना फासले मेरा राज़गी कागज़ी सारी तेरी मेरे सोहणिया सुन ले मेरी दिल दियां गल्लां भटकने ना पाओगे।
Good morning, everyone. Dignitaries present in the room, my dear students and faculty members, on behalf of Department of ECE, Vardhaman College of Engineering, I welcome you all to the inaugural of the conference titled International Conference on Intelligent Systems with Applications in Communications, Computing and IoT 2024. This is organized under Department of ECE, Vardhaman College of Engineering. This conference review has been done very strictly. The conference received a good count of papers, but the acceptance ratio is very less for this because only true research papers have been accepted under this conference. More details and all will be made by the respective general chairs. Now, to proceed further, I would be requesting guests to come on to the dais. I request Dr. GAE Satish Kumar sir, General Co-Chair for the conference, to come on to the dais. It's my pleasure to request our HOD sir, Dr. P. Nageshwar Rao sir, onto the dais. Now I would request our chief guest for today, Dr. Sandeep Chaturvedi sir, General Manager and Head MMIC Design Center, RCI Hyderabad, onto the dais. Thank you, sir. Now, I request Dr. Satish Kumar sir, General Co-Chair, to address all the members present here.
Good morning. Good morning, today's chief guest and head of the department and other heads and deans, faculty of ECE and delegates of the conference and the students. A warm good morning to all of you and welcome to the inaugural session of ICISCCI 2024. So on behalf of EC department, we have initiated this process to organize a conference first in the year 2021. So this is the 7th conference organized by the Department of ECE. In the early days, we used to take the support of the other professors in the Vardhaman or outside Vardhaman to organize a conference that we don't know the process, we don't know the procedure at the time, and we took their help and have successfully organized 3 conferences with their help. Then after that, by seeing all the procedures and process, then we started from 4th conference onwards on our own. But this is the first conference purely done by our faculty. There is no other third person are involved in this, purely done by our faculty. So we took the permissions from the principal and management and support and encouragement from head of the department and the cooperation of all the faculty members of ECE, and a small core team was formed in 8 months back. So we used to discuss and plan and execute it, and at the end of the session we came to this present situation. So this conference we have received 97 papers. Out of them we have nearly 20 from different countries like UK, Scotland, Korea, China and African countries, and 20 papers from Vardhaman and remaining papers from different parts of the country. So the acceptance ratio is we took only 35%, nearly 35 papers were accepted. So this is purely an online conference. All the proceedings of the conference will be published in Springer, and that will be indexed in Scopus and Web of Science. So I thank the management, principal and head of the department, all the committee members, organizing committee members, faculty and students. So to start the conference proceedings today. Once again, thank you very much.
Thank you, sir. Now I request our HOD sir, Department of EC, Dr. P. Nageshwara sir, to share his views about the conference.
So, respected today's chief guest, Dr. Sandesh Kumar Chitravedi garu, and my colleague Dr. Satish, the faculty, my dear students and the participants from various institutions who are there online, and other guest Professor Keshav Dahal, who is also there online. So very good morning to all of you, and I welcome all the students, faculty and researchers to this the international conference ICISCCI 2024. So as Satish told, very good response is there from all the corners of the country. So the main motto of conducting and organizing this type of conferences is give a chance or opportunity to the researchers, students, faculty to share their ideas, to present their findings in a platform. So the purpose of any conference is to tell what they have found, so that the other researchers will be knowing what is actually going, especially after the encroachment of artificial intelligence and deep learning into all the fields. There is a tremendous growth in the research, not only in one particular field, in all the fields, not only electronics, communications, computer science. Okay, it has encroached all the fields. So there is a lot of what you call developments in the special engineering fields. So the faculty, students and researchers, they need to know what is actually going in the engineering field. Simply if they are sitting in a room and start doing work now, it's not correct, because they should know what other research are researchers are doing. So this type of platforms, especially the conferences, will facilitate the researchers to know what is actually going on. That is the main purpose of conducting and participating in the conferences. To my knowledge, participating or presenting papers in the conferences is having more value than publishing a paper in journal. If you write a paper for a journal, okay, people who read it only will be knowing. But when you present a paper in the conference, not only you will be presenting your ideas, but also you will be looking at others what they are doing. So that is the main idea. So previously, a lot of what you call a demand is there for the conferences. Conferences generally we used to travel long distance to present our papers. But after the corona, it was actually true before corona. After corona, people actually stopped going here and there to present their ideas. But once the online system has come, though we are interested to conduct this type of conference in the physical mode, many of the participants are not showing interest to come and present their papers in the physical mode because of their several reasons. They need to travel all the way and they need to stay. Of course, there are several reasons. So though we have mentioned is a blended mode actually we have not mentioned is completely online. Though we have mentioned it is a blended mode, many participants or researchers are interested to presenting the papers in the physical mode will have an edge, definitely. So interaction, actually you might have seen for the last 1 month the number of events are being in the department of ECE. So this is only for networking. So not only to know what others are presenting. Today, Dr. Chaturvedi sir has come. Of course, he is not new to our college. He has come number of times. Last year also he has come. Okay, he's a scientist in RCI. Okay, especially he belongs to RF and microwave. Okay, when people, experts from industry come and give their plenary talks, it will help you to know what is exactly going on in the industry, and it helps you to build the networking. That is the idea of conducting these conferences. As Satish told, this is the 7th one, this is the 2nd one in this year, and 3rd one is there in the October month. So the series of conferences are being organized, being conducted in the department, which helps the faculty, students, and other researchers to know the advancements in the electronics and communication engineering. I request the students and faculty, please make use of this type of opportunities whenever you get, because you cannot go somewhere else to know what is going on. But when, especially when people, experts from industry come and deliver the talks, you need to grab those opportunities. Okay, so he is an expert in RF and microwave, especially in MMIC design, completely related to RF and microwave. So regularly he comes, of course. So please take this opportunity and maximum utilize this opportunity and get the knowledge. So I thank the students and especially the researchers who have presented or are going to present their papers through online for choosing this conference to present their ideas. Thank you one and all.
Thank you, sir, for providing the differences between conference and journals. Both have their own set of advantages. And sir has rightly pointed out, with the different series of events and conferences that we are organizing under Department of ECE, shows you how the department is progressing rapidly. And it also shows the strength of our department. Thank you, sir. Now we have a video message by Professor Keshav Dahal, who is Director of the Artificial Intelligence at University of West of Scotland. He has sent a video message, so the video message will be played now. Just it will be 2 minutes only. Okay, sir.
Hello and good morning to all respected member from Vardhaman College of Engineering, member of the Department of ECE, keynote speaker, paper authors, and all distinguished guests and conference participants. My name is Dr. Kesab Dahal, and I am a professor of intelligence systems at the University of West of Scotland in UK. And I'm also the director of artificial intelligence, virtual communication, and network ABCN Research Institute in my university. I'm the general chair of this conference, International Conference on Intelligent Systems with Applications in Communication, Computing, and IoT, ICISCCI-2024. It's my great pleasure to welcome all virtual and physical participants of this conference. Unfortunately, I could not join you physically and have a face-to-face interactions with you all, but I'm sure you'll have great time and very productive time during these 2 days of the conference. The conference is bringing together expert, researcher, practitioner in the topic of intelligent systems, AI, IoT, communications, and many more. We are in very high time of AI applications currently, and discussion forum like this provides ethical, technical, and practical considerations of integrating AI into different application domain so that these technologies are deployed responsibly and equitably. This event is organized by EAI, that is European Alliance for Innovation, which is a non-profit organization and a professional community established in cooperation with the European Union or European Commission to empower global research and innovations, and also to promote cooperation between European and international ICT communities. And we are very happy to be a part of it. We have a good number of papers going to be presented in the conference. All registered paper will be submitted to publishing by Springer, and also will make it available through Springer Link Digital Library. The proceedings will also be submitted to the inclusion in leading indexing services. With this, I express my heartfelt gratitude for your invitation to lead this conference as the General Chair. And I'd like to thank all members from Steering Committee, Organizing Committee, and Technical Program Committee for their contributions. And also, I'd like to thank to all conference participating members from the EC department of the Vardhaman College of Engineering. And especially, I'd like to take a name, thanks to Dr. Sulaksana Chilukuri for her commitment, hard work to make this conference a success. So thank you once again for this invitation, and I wish you all a very fruitful and inspiring conference. Thank you.
We thank Professor Keshav Dahal sir for sending his video message. Now it's my privilege to introduce our chief guest for today's inaugural session. He is Dr. Sandeep Chaturvedi sir. He has received his PhD in microwave engineering from IIT Delhi. He joined the Gallium Arsenide Enabling Technology Center, Hyderabad, India's only gallium arsenide MMIC foundry in November 1999, where he has worked in the areas of RF characterization of high frequency, active and passive devices and MMICs, measurement, automation, MMIC packaging, modeling and design of state-of-art MMICs. He is currently Deputy General Manager and Head MMIC Design Center in GAE TEC Center. His current research interest and activities are in the field of device modeling, packaging, and MMIC design on gallium arsenide technologies. He has published more than 20 research papers in international conferences and journals. Now I request Sandeep Chaturvedi sir to address the participants and members here.
Thank you very much, Dr. Sangeeta, kind introduction. Very warm good morning to all the participants, online and offline present here. General Co-Chair Dr. Satish, Head of Department, faculty, senior faculty members of Vardhaman College of Engineering, and Dr. Sulakshana, who has been very insistent on me to be here in person. You know, it's always a challenge for me to travel out because a flurry of activities that we have in our small group of MMI Citizen Center. So first of all, I would like to congratulate Vardhaman College of Engineering, ECA department here, always very active and flourishing department, for being able to pull off this conference very successfully. Because doing a conference is doing like marriages, right? Everybody, I mean, those who are little senior enough, they know how difficult it is to plan for any event, social event, where you have to invite people, you have to take care of their hospitality, you have to, there are a lot of technical and non-technical aspect when it comes to conferences. And I couldn't have probably experienced it better, because when I'm doing a conference myself this year as General Chair of Microwave Antenna and Propagation Conference, MAPCON 2024. So it's like a daily struggle on handling different aspects of the conference, getting papers, making sure that good people submit their quality work. I mean, submission of work is not the only thing. Submission of quality work is important. And then you, after getting their papers, you have to reject those papers, many of those papers. So it's like asking somebody to come to your home and then you're, I mean, kind of planning to send them back. So it's very, very delicate affair to handle this part of the conference, getting the submissions and then judging their quality and then making sure that you're not basically disrespecting them. See, when you reject a paper, you're not disrespecting, you're telling them to improvise and come back again, right? So having received over 97 papers, and then you have 35 papers which will be presented over the 2 days. I'm sure a lot of background work has gone beyond all the volunteers. I know only a few names, so pardon me for my ignorance on that. And the keynote speakers which you have pulled up on different areas, because this is this particular theme covers many allied areas like intelligent systems. They are like combination of different types of technology areas, from computing to sensors to communication, a lot of different things. So getting good people to talk about those specialist areas and while still being in the theme of the conference. So a lot of hard work is required to convince people to be part of your conference. Again, with my own personal experience, I can say that. So congratulations on both the parts that you have successfully completed. The third is the conduct of the conference today and tomorrow. I'm sure that your team is capable enough, and under your leadership, we'll have a very successful conference. So with that, I would like to thank all the organizers, management of this college for promoting such interactive events, because as General Chair pointed out, Head of Department pointed out, conferences are not only about reading your paper. They build your personality. When you prepare a subject and write a subject without any foundation, you can do that very easily. Writing answering a question inside your room is very easy. Going to examination room has a different dimension to it, and presenting the same thing in front of a crowd of 100, 200, 300 people is a completely different aspect. and that builds your personality as such. So becoming part of these conferences, of course, in-person conferences are much more higher rated, because then you really get the human feedback, right? People who are listening to you, somebody will be sleeping, frowning, interested, excited, and that whatever has not gone in evaluation of your paper during the TPC phase, that these 10 to 15 minutes of your presentation gives you the feedback for which will drive you to take up that work with more enthusiasm and more value addition in the coming times. So the conferences are a great set of motivational tool for anybody to grow his personality in a given technical area. So I'm sure that the participants online and the students here, especially students, they should take good advantage of the hard work that has been done by this team. And this conference brings you a lot of areas, right? So now you have a complete bouquet of, it's like a bouquet of flowers, right? And you pick the flower that you like. You can pick something on communication, you can pick something on AI, you can pick something on how to apply AI in communication, or how to do intelligent computing systems which will either perform in the back end or on the edge, right? So you're being given exposure. Sometimes we do very themed, very specific conferences which are bound to one single subject or area around that, and sometimes little more generalized conferences. So generalized conferences have a different value, that they give you exposure to a big basket of opportunity, that so that you can pick, okay, this is what I'm going to do. So that's the advantage that you're going to have these 2 days, and take good advantage of it. Do not sleep in between, right? Sometimes you may be there may be some speakers who are very highly knowledgeable, and they will be presenting some topics which may not appeal immediately to you, but then listen to it. After some time, when you listen to similar topic again, you will remember that you know this terminology, right? So go with that open mindset and enjoy the conference. Thank you so much.
Thank you, sir, for your encouraging words. And as sir has said, rightly said, students, you will be gaining lots of knowledge when you attend such conferences, because they present certain papers who are working in certain research areas. Along with that, you have some keynotes also which are delivered during the conferences. Thank you, sir. Now it's the time to release the souvenir of the conference. I request all the dignitaries to come forward for the release of souvenir. I also request Srinivas sir and HODs who have joined here, please come on to the dais for souvenir release. Thank you. Now I request our dignitaries present on the dais to felicitate our chief guest, Dr. Sandeep Chaturvedi, sir. I request our chief guest to felicitate our HOD, Dr. P. Nageshwar Rao, sir. Now I request chief guest and HOD sir to felicitate Satish Kumar sir. I request dignitaries present over on the dais to felicitate the team who has worked hard for the conference. I request Sulakshana ma'am to come over. Now I request JKC sir to come on to the dais, and I request the dignitaries to felicitate him. Praveen sir. These members have worked hard for the conference since past 7 to 8 months. Naresh sir. Give a big round of applause for the team who has been working tirelessly to make this conference successful. I request faculty members who have come over here to join for a group photo. All the faculty members. This is end of the inaugural of the conference. Now it's time for the keynote by our chief guest, Dr. Sandeep Chaturvedi sir. I request him to take over the session now.
So good morning once again. And I've been given about 30 minutes to talk about a specific area, which is probably one of the constituent areas for the theme of this conference. I would be talking about monolithic microwave integrated circuit. So ICs, everybody knows, right? Integrated circuit. So ICs are a combination of one or two active devices, which could be transistors, diodes, or something similar, and then a few inductors, capacitors, resistors, all of them put together in a small substrate. Substrate means a hosting media, right? So that's called integrated circuit, integrated together. That's why integrated circuit, IC. So IC, we know from our general experience that, if you hold a phone, if you hold a radio, everywhere you'll see those multi-legged creatures on the board, black colored ones, right? That's our general perception about the IC. And those are made on silicon, and they perform different kind of digital functions. Something will be doing some counting, something will be doing some addition, simple logic decision making, ORing, ANDing. I think all of this, I am told that most of the people sitting here, they are from third years, so probably in your digital system design, you must have heard of those kind of circuits and functions, right? But apart from those, there are a lot of analog functions also which can be designed in a similar way. And when you want to make a system more compact, integrated circuits are the way they should be done. Otherwise, if you, maybe in the history of computers, you must have read that the first kind of computer used to be almost as big as a room, and today's computer are sitting on the palms, right? So that's the kind of evolution that has happened. And similarly, in the analog world also, for performing different kind of functions, you used to have very bulky systems, space-taking systems, which used to be used for different kind of transmissions, receptions, and all kind of RF signal processing to send a signal to farther distances so that others can listen to you. You can send the information over those high frequency channels. Very bulky systems, bulky tubes, of multi-kilowatt category. Even today they are used in some cases. But then there are a lot of things that can be compressed into very, very small sizes. Some of the examples we'll see in the next 30 minutes. And this is what I do at GATEC, Gallium Arsenide Enabling Technology Center. There are a variety of substrates. I call the substrate is a hosting media. So, and substrate, apart from the mechanical properties of the substrate that it is hosting your circuit, it has certain role in your circuit function. Right, so some of the common substrates are silicon, most common, of course, popular, of course. Then gallium arsenide, gallium nitride, indium phosphide. These are some of the substrates. At GATEC, we work on 3-5 compound semiconductors. 3-5 means the element taken from group 3, like gallium, indium, etc. And then element taken from group 5, arsenic, phosphorus, etc. So a combination of these two gives a specific property to this material system, that it has very high band gap. It has direct band gap, which makes it immune to harsh environments, and they have natural immunity, natural capability to perform better at high frequencies. You can do similar functions. I would not say today. If I was giving this talk 20 years back, I would say that silicon cannot do it. But today, I cannot make the same statement, because silicon is also equally going in frequencies beyond 100 gigahertz. So, but then silicon does not have the natural capability like compound semiconductors. So you have to do a certain improvisation in processing of silicon to make it compatible for working at high frequencies. So our mandate is to work on 3-5 semiconductors which have natural capability for high frequencies and harsh environments, especially for defense and aerospace applications. When any circuit is flown out in space, it has to face extreme cold, extreme hot temperatures. It has to face radiations of 100 kilorad, 30 kilorad to 1 megarad, proton, a different kind of radiations. So your circuit should be such that it can survive those kind of environments. And gallium arsenide and similar kind of compound semiconductor material have that capability because of the direct band gap structure. So at GATEC we have, this is the only production foundry in India. We are very proud of this status. I'm sure in the coming days probably some more foundries might come up with the government support, but today we are the only one who are in production. There are some R&D facilities, but production, like we take user specification, we design around that, put them to the packages in required form, and then give it to for their applications. So these MMICs will be used in satellite signal processing chains, RF signal processing chains. They will be used in missile systems to guide the missiles to designated targets. These will be used in radar systems to enable them to track objects in farther distances. These distances could be 100 kilometers to 1,000 kilometers. Right? So variety of functions can be realized, and we keep doing regularly for different DRDO and ISRO projects. So we talk of different node sizes: 0.7 micron, 0.5 micron, then 0.25 micron, 0.13 micron. So the latest thing that we do at GATEC as of today is 130 nanometer or 0.13 micron gate length pseudomorphic HEMT device. The human hair is about 5 to 10 microns. So you can think the gate that is sitting inside the transistor with a gate length of 0.13 micron, which is roughly 10 around 50 times thinner than your hair. Right? So that's the kind of criticality in production of these technologies. And these technologies, we are proud to say, these are done indigenously. These high-tech things are not available easily from outside. So these have been developed, and they have been put to production. Other than gallium arsenide, we also work on gallium nitride, which is another important technology, because when we want to do power amplification for high power transmissions, you cannot live with devices which give only low power. So as I always say, like power is voltage into current. So to increase power, either I can increase current, right? I can pump more and more current, put more and more devices in parallel, and then generate more power. But then I'm increasing my circuit size, and then beyond, and then when I combine, there are losses in the combiner, and that would take away the advantage that is coming from the successively adding these devices. So adding current is not very useful technique. I mean, though it is used, but not the best technique when it comes to comparison. So the other thing is to increase voltage. Now, how do I increase voltage? Any given device will have breakdown. So there are source and drain contacts, and I am going to apply the voltage VDS to make the current flow in the channel. And then I'll put a gate electrode to control the flow of that current. Now, how much voltage can this drain source contacts withstand is dependent on my material. So gallium arsenide in general can be, when the best kind of gallium arsenide devices can be made to withstand about 20-25 volts. That means in all conditions of operation of my device, the voltage should not exceed 25 volts. It means I can apply all at the most 8 to 10 volts, because when we do amplification, if you see the IV curve of the transistor and you superimpose your AC signal on the DC IV current voltage transfer characteristics, forward characteristics, the voltage, AC voltage generally goes twice to 2.5 times of the applied VDS. So for a device, one of the best devices that has, let's say, 25 volts of breakdown, I cannot apply more than 8 volts. So that is my limit on the technology in terms of voltage. So what should I do? I have to look for another material, and gallium nitride is one such material which has, because of the higher band gap, so gallium arsenide has a band gap of 1.4 volts, and gallium nitride has band gap of roughly 3.4 volts. So this large band gap enables higher breakdown voltages to the tune of 100 to 200 volts, That means I can operate my device at anywhere between 20 to 50 volts, right? So immediately my capability from 5 volts of operation has increased to 50 volts of operation, and that's a direct impact on the power delivery. So I can generate power densities which are 5 to 10 times higher than the gallium arsenide devices. So that's one which we are working on, and this is the talk of the town today, because slowly we are trying to replace the bulky tubes which are used for high power transmission by these solid state devices. So if I can make a device which has, let's say, 100 watts, these numbers were unthinkable about 10 years back, because we used to say that solid state devices are not good for more than 10-20 watts. So today, with gallium nitride, we can do devices which are in the range of 100 to 200 or 300 watts. And these are very, very tiny devices. Less than, if I take a 100 watt transistor, it will not measure more than 1 millimeter by 2 millimeter. So can you imagine just holding a 100 watt incandescent lamp? It is this big, right? And then we are compressing that 100 watt in a very small area. So it's an achievement and it's a challenge. Achievement because we have been able to compress a big thing into a very small, tiny size. But the challenge is, out of this, when I produce this 100 watt, I'm also spending something like 200 watts. Because no device will have ideal conversion from DC. Amplification is basically conversion of DC voltage into AC voltage, in a sense. You apply a very small AC voltage at the input, and the DC voltage gets added, and you get amplified AC voltage. The best of the devices can be around 70% efficiency. And if I do a multi-stage amplifier, power amplifier, because I will not be running all the stages at full efficiency because of linearity limitations. Because when I run at saturation, I'll also generate, other than my main carrier, the harmonic frequencies also I'll generate. So normally the driving stages will not be run at high efficiency. So typical efficiency for a multi-stage amplifier will range anywhere from 30% to 50%. That means 50% of the applied power is getting wasted. Now imagine managing 100 watts of power which is concentrated in 1 millimeter by 2 millimeter area. You have to channel that out. If you allow it to remain trapped there, your device will fry immediately. If it was an egg, it will become an omelet, right? So this is a challenge. So and there are different techniques which are used for managing this kind of scenario. Can you go to the next, please? Next slide, please. Next slide. Keep going, keep going. Okay, stay. We just talked about what an integrated circuit is. In the microwave domain, when we make the integrated circuits, there are two ways we can make these integrated circuits. I can take components which are capable of working at these frequencies. I have to be, careful about their sizes so that the parasitics are not very high. And then I can put them together. I can make a layout on a PCB with copper foil, right? And then mount all these components on top of that substrate. So that can also make an integrated circuit. Of course, it's not the true integrated circuit, I would say. But then everything is together in a single substrate. So this kind of circuit is called hybrid microwave integrated circuit. Hybrid means it has discrete components, but the routing or the interconnects are on the substrate. And then, in fact, you can also do some integrated circuits itself, which can sit on the substrate. So it's a hybrid scenario. Advantages are when one single function, when there are multiple functions to be performed from the system that you're trying to design, it may not be always possible to compress them all into a single chip. So such multiple chips and some discrete components can be put together on a substrate. It could be a two-layer substrate or a multi-layer substrate, depending on what is the complexity of signals that are to be supplied to the chip. And that makes a hybrid integrated circuit. On the contrary, the MMIC, monolithic microwave integrated circuit, will have everything, each and everything that is required for functioning of that particular chip on the same substrate. So one, let's say 2 by 2 millimeter or 4 by 4 millimeter chip will have all the essential transistors, all the inductors, capacitors, resistors, and interconnects. So what you need to provide additionally is connection to the outside world, which will be done through the gold wires or copper wires or aluminum wires, as the case may be. And then, but otherwise, the IC is more or less self-sufficient, right? So that is what MMIC is. We will see what is the extent we can go from single function scenario in a IC to the multifunction scenario on a HMIC. How much of MMIC can take from HMIC in some examples later on. Next one. So materials which are used for HMIC or MMICs are like, if I am doing MMIC, my material choices would be silicon or one of the compound semiconductor materials like gallium arsenide, indium phosphide, etc. Silicon carbide, this is also used in some applications for high power switching. Silicon germanium is again one popular material, is a compound 2-4 semiconductor, and then it gives additional edge over silicon because of this analog functionality added because of this. Then gallium nitride is material which is used only as the channel, but then you have to have a host substrate. So we have gallium nitride devices sitting on silicon substrates for cost benefit and CMOS compatible integration, and gallium nitride on silicon, which are very high because silicon carbide is a very high thermal conductivity substrate, because I mentioned about the heat that has to be dissipated out. Okay, so silicon carbide can offer the right media for channelization of that heat to the heat sink. So when it comes to very high power and very high frequencies, gallium nitride on silicon carbide, this is one of the materials that we use. Next one, please. Now to design an MMIC, this is the typical flow that we have to go through. So you start with the design specifications. We choose an active device technology because let's say if I'm working on amplifier design, so I must know whether I have a right transistor which has sufficient gain, because this is what you want to do from the amplifier, which has sufficient gain at that particular frequency or not, whether it has sufficient amount of power that can be delivered to the next stage of the transistor. So we choose that particular device. Now once you have chosen the device, you have to decide, if you have seen the forward IV curve of a transistor, you can vary the control voltage or gate voltage from the pinch off threshold voltage to full current. Now, where should I bias this transistor so that it gives me right amplification, the kind of amplification that I am looking for? So deciding that bias point is again depending on application, we decide whether I should keep in most cases you want your sine, if you're giving a sine wave in, you want a sine wave out without too much of distortion, right? So if I want to do that kind of thing, my obvious choice would be to sit on right at the middle of the IV curve. Okay, and that is called class A bias or linear class bias. Similarly, if I am looking for very high efficiency, then I would try to minimize the current, right? So when you want to minimize the current, that means you will be doing a deeper bias towards pinch off. So I'll be sitting towards bottom of class B and class C will be towards bottom of the IV curve, and then device switches on only if there is a sufficient input signal strength. Otherwise, it remains quiet. This gives lot of advantage in terms of power consumption, standby power consumption, but it has its disadvantages that it is very rich in harmonics. It is it reduces the gain because the device is not always biased, so it reduces the gain by 3 to 6 dB. So we select the bias, and then once you have selected the bias, each device will have certain frequency response. In general, the DC gain or low frequency gain will be very high, and then it tapers off at third, a certain amount of power delivery. So we can do either match which is specific only doing gain amplification in terms of gain, voltage gain, or we can do match to the exact load, optimum load of the device, so that I also gets meaningful power out from the device. So depending on where I'm going to use this amplifier, whether somewhere in mid of the chain of RF or at the final end, I decide either to match for gain or match for power. Or if I'm doing a receiver, I can match for noise, so that the sensitivity of the receiver is very high. So we do that design. Now, most of this first step design is using ideal inductors, capacitors, and resistors, right? Just to get a good feel that, okay, I have, quickly I can get gain and the required band response. Immediately after that, because those ideal components are not something which you can realize. So you have to replace those ideal components with the library components. Library means it's a representation of the physical device that will be printed on the substrate, realized on the substrate. So those electrical models will be replacing your ideal inductors, capacitors in the next stage of design. And then obviously what happens, inductor is no more an inductor. It also has some capacitor. We'll see just an equivalent circuit later. Capacitor has some inductance and the leads and some resistance, some feedback part. So your matching, entire matching gets disturbed. So we need to re-optimize all this cycle. The next stage is to add, initially we do all connections by ideal wires. Like ideal components, the connections are also ideal. So we do replace those connections with physical transmission lines. Now the moment you do, put those transmission line, you will have to use some bend somewhere, some T-junction somewhere where you have more than one branches joining a point, or a cross somewhere. So when you add these components, again your matching net, because all these are going to contribute some inductance or capacitance, okay, in RF domain. So again your matching gets disturbed, and then you retune all the physical inductor, capacitor, resistor values to get back your matching to the shape, and then we generate the final layout of the disk. Now once the final layout is ready, because this component is going to work at high frequencies, and high frequencies, if there are two inductors sitting like this parallel to each other, there is a coupling going to happen. And this coupling is dependent on how close they are and how what is the length that they run parallel to each other. So we had to run, we discretize the whole layout space into very, very tiny parts. We call it meshing. And then you can see probably the lower right corner. So we mesh that space or discretize that space, and then solve current voltage equations or Maxwell's equations for each part of the circuit, and then get the interaction matrix between different parts of the circuit. So there'll be a lot of situations where you're like without layout, your circuit is working very nicely, very nice flat band response. But then the moment you put the layout and you do EM simulation, because the EM simulated response is the one which you are likely to get in the reality, because that then kind of computes all the interaction between adjacent components, lines, and etc. And then you will find that some inductor which is not part of input matching network, it is coupling with the input network, and your input match has got disturbed, or some inductor is causing excessive feedback in the device, and the device, the amplifier gain has reduced. So we need to retrade these scenarios and then come to a final design shift. So that's the whole cycle. It can take many months depending on the complexity of the circuit. The simple amplifier I can design in a month's time, but there are circuits which can take 5 to 6 months depending on the coupling scenarios, basically. Next one, please. Yeah, so this is what I meant to say, the ideal versus real components. So when I replace an inductor with a physical inductor, it also has a resistance from the track. It has interwinding capacitance that will come into play. Similarly, a capacitor will have a parallel resistance to the prime capacitance. It will have some inductance in the leads. So when you replace an ideal component with a physical component from the library, all these get added and then modify its behavior in the circuit. So we need to understand that behavior and then carefully detune that effect and then get the right performance. Next one, please. Similarly, if I can assess the behavior of a component which is independent of the frequency, then I call it a lumped component. But then if the behavior is changing with frequency, it is no more lumped. It becomes a kind of distributed behavior. So my lumped part is limited to a very, very small section of my layout, and then I have repetitions of those lumped sections which form the overall response of this device. So whenever any part of your layout becomes comparable, the limit we normally say is lambda over 16, right? So if any component size is more than lambda over 16 in the layout at the given frequency, then you have to take care of its distributed behavior, and then only your circuit will perform as per your expectation. Next one, please. Next one. These are typical MMIC functions that we normally design for any kind of signal processing applications, RF signal processing application. You will have to modify its amplitude. You will be either increasing the amplitude or controlling the amplitude or reducing reducing the amplitude. You can modify the phase of the component so that the typical application could be MIMO or beamforming. You want to do different phases and different elements and form a narrow beam which can be steered. You will be doing frequency manipulation. For example, I have a low frequency source, let's say C-band source, and I want to generate a frequency in Ka-band. So I need to multiply this frequency by let's say 4 or 5 factor to generate a signal in 24 to 30 gigahertz band. So these circuits, frequency multiplication circuits can do that job. And we use the nonlinear behavior of the device so that I describe my current equation with voltage versus current equation to the second factor or the third factor. And then that factor gives me the additional tones that can be used to generate the higher frequencies. And then once I have got a device which is performing at generating those tones, I can filter out the remaining tones which are not required, and I get the pure signal at a frequency. Okay, next one. Then another thing is switching. You want to make switch path selection between TX and RX. That's one of the most common applications. Or multiple antennas are connected, and then you want to switch between those antennas or switch between those receivers. So these are some of the functions that are normally designed in MMICs. Next one. Next one. So probably somebody would ask why I titled my talk from megahertz to terahertz. You know, a design is a design. You know, whether I'm doing a few hundred kilohertz or few hundred gigahertz, I have to follow the same, respect same Ohm's law, same Kirchhoff's law, same Maxwell's laws. So what makes it different when I transit from a very low frequency to very high frequency? Is my low frequency design really simple? Or is my high frequency design so complex that I should be afraid of? No, it is not so. Each design comes with its own challenges and a set of mitigation techniques that have to be followed. So I just listed 2 or 3 scenarios here. When I am doing at very low frequencies, less than a gigahertz, right? 1 gigahertz, all my inductors, capacitor values, when I synthesize the matching network, all my inductors, capacitors will run into multiples of multiples of tens of nanohenries. Like I'll get inductor values in 10, 20, 30 nanohenry. Capacitor in more than 10 picofarads. Now these values cannot be realized on MMIC because this consume lot of real space. So then I have to do an optimum combination of what to keep it on the chip and how much I have to go outside the chip. So that is one of the mitigation techniques. When I use very high inductance and capacitance values, these will have the self-resonant frequency because of that model that we saw, because each capacitor is also having some inductance. And after SRF, capacitor becomes inductor, inductor becomes capacitor. So we have to take care of such scenarios when we are doing low frequency designs. Fractional bandwidth can be very large for a given physical bandwidth. If I'm designing 50 megahertz bandwidth at 1 gigahertz or say 500 megahertz, it makes sea change, right, in terms of percentage bandwidth. And all these networks, when we design, depending on their order, they given certain fractional bandwidth. So if I have requirement of a certain physical bandwidth, my network order may have to be increased to cover the given fractional bandwidth. If I go to higher frequencies, my challenges are that all my component sizes that I'm going to use, the inductors, the capacitors, resistors, interconnects, they start becoming comparable to the wavelength. They start violating that lambda over 16 rule. So that means I have a lot of parasitic behavior from these components, and there are frequencies. For example, if I design something at beyond 60 gigahertz, beyond 70 gigahertz, I cannot use my lumped spiral inductor or the capacitor, because it will have so much of parasitic overload that it will no more act as an inductor. So I do not get the inductance behavior, so why should I use it? So I'm not allowed to use such things which can be used in low frequencies. So many of those things will be then realized by line sections or open stubs or shorted stubs to realize the inductance and capacitances. And one more thing that is very important in, of course it is important in all frequencies as such, but then it becomes more and more important as you go at higher frequencies, because your mesh size has to be sufficient enough that whatever trace you have drawn or whatever metal feature is there on your design, it should have at least certain mesh cells, certain number of mesh cells, so that its behavior is properly modeled. So as you go higher in frequencies, your mesh size has to be smaller and smaller, number of mesh elements grow, and then it becomes more longer simulation. So that is one of the challenges. Go on. Go on. Keep going. So there are a lot of things. I think the time is not going to be sufficient if I start talking about all of this. I'll just go to the last slide. Keep going. Yeah, stay. So this is one typical example. Here, I think I started in one of the slides, HMIC versus MMIC. In that, if you remember, I don't know how many of them will remember, but if you remember, there was a single function. I just showed an amplifier over there, and the HMIC had a lot of different things in it. Now if you see this is also an MMIC, and this MMIC comprises about 9 different functions. It has got 3 plus 2, around 5 amplifiers, 3 switches, 6 phase bits in a phase shifter, 6 attenuation bits in an attenuator. So roughly 9 overall functions, but 20 different circuits. And something like, of course, compared to silicon, we are still, in minuscule, but then something like 100 to 150 transistors. Now for this chip to work, I have to make sure that all the lines crisscrossing each other should not allow the signals to leak through. I have very low signal that is going to enter from here, which will be amplified and then routed to the switch to this section, which goes to attenuator, phase shifter, goes to the top switch, and then comes out for the receive. For the TX, it enters here. Again, it gets passed from this section and then emerges from that side and further amplified. So there is lot of signal. The RF signal itself crossing like TX and RX sides. There are a lot of DC signals which are required for running, controlling the phase shifter and attenuator, 6 circuits each. So 12 plus 3 switches. So roughly 16 signals, they crisscross through the chip. And if you do not take care while they are passing underneath each other, because when the crossing happens, it is through a dielectric, right? Like otherwise it will get short. So if I do not take care of the correct technique for this crossing, entire RF signal can get leaked. and I am varying the attenuation, but nothing will happen. You'll have some static performance. In fact, we had a very practical experience of ending up in such a terrible scenario. And then we understood why that happened. We fixed it, and then when we went for a respin of this particular design, we got all the functions doing the right job. So what I meant to show here is that when you design, the complexity levels increase, and then your understanding on what is causing a particular behavior. Whether when I am trying to amplify, whether I am getting the meaningful amplification or not, that needs to be understood and then mitigated. And the techniques are the primary technique here when it comes to multifunction integration. So now if you compare this, this is a complete TR module. If I compare this tip with a HMIC module, it will be almost like your A5 size diary, right? Roughly 200 mm by 80 mm. Now that 200 by 80 mm I have compressed into 5 mm by 5 mm. That's the kind of compression that is possible. This is still not the best, I would say. There may be still some scope to reduce it further. To pack more, this is a single channel TR module. To pack more channels into this, today time is not sufficient, otherwise I would have shown that some of the silicon RFICs working at 200 gigahertz, 240 gigahertz, 140 gigahertz, compressing anywhere from 4 to 16 channels into a single beamforming channels into a single chip, along with the up conversion, down conversion circuitry, all in a space of something like 4 by 4, 5 by 5. And why I talk about these sizes bigger than this cannot be supported by these substrates. These are very fragile, very thin substrates, so they will break down. So, so this is to just give a glimpse of what is involved in MMIC design. This is only a minuscule part of the overall theme of this conference. Many of these things are needed when you talk of intelligent systems. I'm sure that the speakers in the rest of the day and tomorrow, they will take you through many of such interesting concepts, and then you can form an overall view how an intelligent system, how a communication system works, and how you can contribute, how you can make your own designs, what to look for, what to avoid in such systems. So I hope that, I'm not sure whether you have captured all that what I spoke about, but I am sure that it will probably trickle some curiosity that you will come back to someone like me with more questions. So with that, I would like to thank for patiently listening. I can see some people sleeping. I can understand why they, right? So I'm sure that in the coming days that you'll generate more interest on such topics. They are very exciting. When you see your chip, you design an amplifier. Remember, I mean, I have not talked. I will take another 2 minutes probably. So if you design an amplifier and then it goes up in the satellite like Chandrayaan, do you know what kind of feeling you'll get? You'll have butterflies in the stomach. So we design these ICs day in, day out, and every year, typically 4 to 5 satellites, they take these MMICs up in the sky, or they become part of some aero defense system, and the kind of intoxicating feeling it gives is unimaginable. So if you start taking interest, I would not talk much about the other subject, as I'm very focused on what I do. So if you start taking interest in this, you'll find that it really does not let you sleep. When you design a particular circuit with certain application in mind, that this is where it is going to work. It is going to fly in something like Chandrayaan, Aditya, the Mangalyaan, or some of the missiles. It's an amazing feeling that you'll get. So I hope that some of you will get intoxicated like me again, and then become good designers in the coming future. Thank you so much.
Thank you, sir, for taking out your time. We know actually how busy sir is. And as sir was saying about his passion, right, when he works in this area, that sort of having a butterflies in the stomach, when that thing works and flies into the space, you yourself also can imagine, you can also work in this sort of areas. Thank you, sir. Now this is the end of the inaugural session of Complete the Conference. Now I hand over to the Sulakshana ma'am for the National Space Day celebration. Please be seated. We are having another session following.